My paper ID. My co-authors are the Dr. Aparesh Datto, Dr. Nirmalendra Vishwas, Professor Dr. Nirmal Kumar Varna. I am from Department of Technical Education and Training, Government of West Bengal, in Mednipur Sadar Government Part Unit in the Mechanical Engineering. My presentation plan, the first of all introductory section, next of the objective and scope of studies of the problem geometry and some boundaries, conditions, mathematical models, analysis, research and discussion, which includes effect of Richardson number, impact of Hartmann number, nanofluid particle volume fraction, impact on the flow, and heat transfer characteristic analysis. Finally, that is the concluding remarks. The introductory section, MHD mixed convection, is the key challenges in the budding engineering problems, includes porous media, and translatory motion also includes the influence of magnetic field. There are several applications in the engineering problems that like MEMS, heat exchangers, etc. And all translation motion also induce the shear flow structure. Usually in many applications, the conventional working fluid like air, water, glycol fails to fast response in the thermal process like heating, cooling. But with the inclusion of nano-sized conducting materials like copper, alumina, etc., with the base fluid shows considerable improvement in the heat transfer process, and also the imposed external magnetic field can effectively control the hydrodynamic behavior. It has also lessens the heat transfer rate, but it has got several industrial applications. On the perspective of the above, MHD combined free surface as well as forced convection, free or forced convection of a nanofluid filled porous cavity called PDC in tertiary wall heating. Objective and scope of work in that MHD mixed convection in that PDC with surface nanofluid saturated porous as well as forced convection along with the externally imposed magnetic field convection has not yet been studied as far as our literature survey concerned. PDC in tertiary wall heating is formulated and motivated by the need to analyze the scope of thermal flow and heat transfer in that performance MHD mixed convection under in that PDC with surface nanofluid saturated porous as well as forced convection the system along with the externally imposed magnetic forced convection has not yet been studied as far as our literature survey concerned. PDC in tertiary wall geometry of the classical motivated by the need to analyze the scope of thermal flow and heat transfer in that MHD mixed convection under in the PDC regimes with surface nanofluid porous as well as forced convection the system along with the externally imposed magnetic forced convection has not yet been studied as far as our literature survey concerned. PDC in tertiary wall geometry of the classical motivated by the need to analyze the scope of thermal flow and heat transfer in that MHD mixed convection under in the PDC regimes with surface saturated porous as well as forced convection the system along with the externally imposed magnetic forced convection has not yet been studied as far as our literature survey concerned. PDC in tertiary wall geometry of the classical motivated by the need to analyze the scope of thermal flow and heat transfer in that MHD mixed convection under in the PDC regimes with surface saturated porous as well as forced convection the system along with the externally imposed magnetic forced convection has not yet been studied as far as our literature survey concerned. PDC in tertiary wall geometry of the classical motivated by the need to analyze the scope of thermal flow and heat transfer in that MHD mixed convection under in the PDC regimes
When cancer is that convection of the physical of the internal has not yet deteriorated as now or PTC.
buoyancy is higher. Magnetic field counteracts the magnetic field so that the heat transfer rate is decreased. And here the Nusselt value is quite decreasing. Inclusion of the nanoparticles impact is visualized here. There is no particle and there is particles in 2% and 5% of the copper metal particle. The structure of the fluoride and atom or energy almost the same, but here the Nusselt value is increasing. That means some enhancement in the transfer due to the particle inclusion of the with the base order. Heat transfer characteristic features with the varying Richardson number with Hartmann and nanofluid particles. Here with the increment of the Hartmann number, Nusselt value decreases, and with the increment of the nanofluid particles, that is the heat transfer characteristic means Nusselt value increases. That increment, that means the enhanced features of the increment of the copper nanofluid particles is above the second point number, means at higher Richardson number, whereas the 13.45% increment of the nanofluid particles, that is the Hartmann number. Transfer characteristic means Nusselt value increases. Concluded by increment, that means the enhanced features of the increment of the copper at higher Richardson number compared to lower Richardson number. Initial convection occurred at higher Richardson number. Almost 13.45% decrement of heat transfer occurred in higher Hartmann number, which equal to 100 compared to low magnetic field. In addition, inclusion of the as the substantial increment of the heat transfer due to the increase of thermal conductivity transfer enhancement rate is 0.77 to 7.51 compared to base fluid. In the inter-analysis subject PDC can afford valuable insight for conducting and controlling the heat transfer process in the thermal cavity as the potential future work under multi-physical conditions. The references and questions. In the inter-analysis subject PDC can afford valuable insight for conducting and controlling the heat transfer process in the thermal cavity.
Hello, sir.
So should we move on to the next video or we pause for some time?
Yeah, I mean, after one video there will be question answer session. Then we will play the next video.
Break where
Yes, sir.
keep this particular screen and session share will ask for.
Yes, sir. So yeah. Hello, sir. So I'll play the next.
Yeah, we already have on the screen. You can play the next.
Yeah, I mean, yes, we'll play the next video. There will be question answer session. Then we will play the next video.
Break where
Yes, sir.
keep this particular screen and session share will ask for.
Yes, sir. So yeah. Hello, sir. So I'll play the next.
Yeah, we already have on the screen. You can play the next.
Yeah, I mean, yes, we'll play the next video. There will be question answer session. Then we will play the next video. Yes, sir.
Keep this particular screen and session share.
Yes, sir. Yes, sir.
Yeah, so is it visible on your screen, sir?
Yes, please visible.
Yes, sir.
Good morning to all of you. I am Professor Uttam Kumar Sarkar from Mechanical Engineering Department, Technomin Salt Lake. Today I am going to present my work on natural convection in a semicircular enclosure.
Yeah, so is it visible?
Internal free convection has been a topic of intensive research because it has ubiquitous presence in natural processes, engineering applications, biomedical systems, and so many other applications from mechanical engineering department. Further, it presents an intricate coupling between the flow and transport processes, which often lead to a rich variety of flow patterns. There is an enormous pool of literature on the natural convection of different rectangular or square enclosure. In comparison to that, natural convection transfer on different non-rectangular enclosure is a relatively new subfield in the heat transfer research, and so many other applications. It is to be noted that the enclosure with non-rectangular cross-sections such as triangular or parallelogram section have several practical applications. Recently, Duff et al. Reviewed the natural convection in different non-rectangular cross sections such as triangular section, trapezoidal section, or parallelogram section. With that, we come to the main motivation of this study, that is, after a detailed literature survey, it has been found that natural convection in a semicircular enclosure which is being heated from the bottom is not studied yet. It is to be highlighted that the analysis of natural convection is not a matter of course. It has important applications for the design of nuclear reactor, heat exchanger, electric cooling system, etc. So the main objectives of the present study can be summarized as follows. The first one, to numerically analyze the natural convection phenomena in a semicircular cross-sectional enclosure which has an isothermally heated flat base and isothermally cooled semicircular top surface. Further, the study presents the effect of variation of Rayleigh number on the evolution of gross and thermal field inside the enclosure for a fixed value of Prandtl number, that is Prandtl number equal to 1. And last but the most important objective of the study is to determine the different steady solution branches that evolve as the Rayleigh number is varied. Further, the study presents the problem formulation. Figure 1 presents the schematic diagram of the problem. So there is a semicircular enclosure, the bottom flat surface of the enclosure is heated and the top surface is cooled, as shown in the figure, and gravity vector is from top to bottom as shown in the figure. We assume a steady laminar two-dimensional flow of an incompressible Newtonian fluid, and we apply the Brownian's approximation. We take the non-dimensional Bernoulli equation can be given in standard form, and equation 1 to 4 is governed by two non-dimensional parameters, that is Rayleigh number and Prandtl number, and for this study Prandtl number is fixed, so the solution is mainly governed by the Prandtl number, and the boundary conditions are of the flow is already specified in the dimensional form in the equation, and non-dimensional form it is given in the bottom of the slide. Coming to the numerical procedure that is used for obtaining the solution of the problem. So solution of the thermofluidic problem is obtained using the finite code of ANSYS, and the boundary conditions are a repeated course mesh that is used for discretizing the computational domain is shown in the figure, and it can be seen that the computational domain is partitioned so that we can obtain a structured mesh, and the map phase matching technique of ANSYS is used to generate the structured mesh with all the coordinate elements. And the heat independent study is conducted, and the study is conducted for the maximum value of Rayleigh number that is studied, and that value is R is equal to 5. And for that maximum value of Rayleigh number, it has been found that if the number of elements is approximately 1 lakh, then the error in the solution is less than 1 lakh. So this particular treat is used for all values of Rayleigh number, which is less than equal to R is equal to 10 to 5. The second order upwind method is used for discretizing of convective terms, and the simple algorithm is used for pressure velocity coupling. Specific interpolation is used to compute the phase values of the pressure from the cell values, and to ensure the accuracy of the solution, iteration is continued till the residuals of all the governing equation is less than 10 to the minus 6. second order argument method. With that, we come to the results of this study. First, it's noted that for all values of value number that is studied, the flow structure appears in the form of a pair of counter-rotating convection cells. So the two-cell solution, which is found for all the values of value number, is shown in the figure 3. So in figure 3 we present the contours of stream function as well as contours of static temperature. So first column presents the contour of stream function and the second one presents the isotherm for different values of value number. So the top row represents the lowest value of value number, that is Ra is equal to 10 to the 3, and the bottommost row refers to the maximum value of value number 10 to the 5. In between we have the intermediate values of value number. So if we refer to the Ra is equal to 10 to the cube, 10 to the second one isotherm, it immediately appears that the temperature conduce is due to the conduction heat transfer. Now, as value number is increased beyond 10 cube, and we can see that the temperature distribution gets deviated from the case of conduction denominator case of Ra is equal to 10 cube. And the deviation is becoming more and more as the value number is increased. Further, it is noticed from the contour of stream function, as the value number is increased, the convective motion, intensity of convective motion inside the cell increases. And the last, we can see that the x is equal to 0 line represents a virtual wall, adiabatic wall, which doesn't allow any cross flow and it doesn't allow any lateral heat transfer to take place. The most important finding of this study, that is, as we increase the Rayleigh number, after a critical Rayleigh number equal to approximately equal to 22,000, apart from the two-cell solution, there is a second steady solution which appears in the form of two pairs of counter-rotating convection cells. So the fourth cell structure that is obtained beyond Ra is equal to 22,000 is shown in the figure 4. And if we refer to the streamline and the isotherm for this fourth cell structure solution, we can see that as the Rayleigh number is increased, the shape and size of the convection cells are changed. Particularly, as the Rayleigh number is increased, the size of the central convection cell continuously increases, whereas the cells which appears at the side of the enclosure gets squeezed. Along with the increase in size of the convection cell, it is further noted that with the increase of Rayleigh number, the intensity of the convective motion also increases inside the convection cell. And if we refer to the contour of the isotherm, we can see the upward and downward plume-like structure, and this upward and downward plume-like structure can be correlated to the lines of cells which have zero value. So for psi value of 0, we can have this upward and downward plume-like structure, and this upward and downward direction is further correlated to the direction of the flow. The direction of the flow is vertical or upward along the psi equal to 0 line, then there we have a upward plume-like structure, and vice versa. Okay. And further, it is noted that with the increase in Rayleigh number, we can have this upward and downward. The isotherm gets progressively crowded near to the boundaries, and that can be very much evident for higher values of Rayleigh number. So with the increase of Rayleigh number, the temperature gradient near the wall increases, which implies the heat transfer also increases near the boundaries as Rayleigh number is increased. So here, in this slide, we present the summary of heat transfer characteristics for the two-cell solution and the four-cell solution. From the figure 5, we can see that average natural number always increases as the Rayleigh number is increased. However, the rate of increase varies for different range of Rayleigh. Particularly, it is noted that for a very low value of Rayleigh number, that is, say, Rayleigh number is less than 2000, natural number remains almost constant with respect to the variation of Rayleigh. So this insensitivity of natural number number with respect to rally number for a small value of rally number may be correlated to the heat transfer characteristic that is present for low values of Rayleigh number, and we have already discussed that for low values of Rayleigh number, heat transfer phenomena is dictated by the conductivity. And further, it is noted that Nusselt number for 4-cell solution is always less than the Nusselt number for a 2-cell solution, and this fact is further corroborated from the contours of the Cymax, and we have seen that for 2-cell solution the Cymax value is always higher than the 4-cell solution, which means that intensity of convective motion is always greater for 2-cell solution. Consequently, the rate of heat transfer and the Nusselt number is higher for the 2-cell solution. We come to the conclusion of this study. So the first conclusion is that steady state solution with two counter-rotating convection cells exist for all values of Rayleigh number that has been studied in this investigation. Secondly, it has been found that steady solution of the problem is non-unique. Particularly, it has been noted that as the Rayleigh number exceeds the value of 22,000, there are two solutions. Apart from the 2-cell solution, there is another solution with 4-cell appears, and that persists as long as Rayleigh number is greater than 22,000. That has been studied in this investigation. And from the from the graph of the average Nusselt number, it has been noted that Nusselt number always increases with the increase of Rayleigh number. It has been noted that as the Rayleigh number for very small value of Rayleigh number, for 2-cell solution, Nusselt number remains almost constant with respect to variation of 4-cell appears. The last one, the value of Nusselt number, average Nusselt number for 4-cell solution is found to be smaller than the corresponding value of 2-cell solution. It has been noted that Nusselt number always reference increase of Rayleigh number. It has been noted that as the Rayleigh number for very small value. Now I open the session for question and answer. Nusselt number remains almost constant with respect to variation of 4-cell appears. The last one, the value of Nusselt number, average Nusselt number for 4-cell solution is found to be smaller than the corresponding value of 2-cell solution. It has been noted that Nusselt number always reference increase of Rayleigh number. It has been noted that as the Rayleigh number for very small value. Now I open the session for
Abhijit, I am logging out now. If you want, you can carry on, but we already had the 30-minute session. So,
am I audible, sir?
yeah, you are audible.
Okay. I just wanted to check that. I have no problems in joining. I just wanted to know if the audio is okay. Now I can leave, no problem, sir.
Yeah, you should leave actually. This is not open session. We are just having some trial runs.
Yeah, okay. Actually, in the mail it was said you can check if you can join. So that is why. Okay. Thank you.
Fine, thank you for
Am I audible, sir?
Let us see you tomorrow. Definitely, you are audible.
Yes, sir.
Okay.
Yes, sir. I just wanted to check that. I look forward to problems in joining.
Yeah.
I just wanted to
Same
know if
here.
the audio is okay. Now I can leave, no problem, sir.
Yeah, you should leave actually. This is not open session. Vijit, I am logging out now.
Yeah, okay.
So,
Actually,
you
the
can
mail it was
continue or
said you can check if you can join.
Yes. I'll continue with other buts.
Sure. I am logging out. But
Yes.
two
Yes, sir.
videos
Yes,
that I
sir.
saw, they
Definitely
ran
check that.
properly.
Look
No
forward to
issue.
problems in joining.
Sound quality
Okay, sir.
was also good.
Audio is okay.
Yes. Yeah. Sounds good.
Now I can leave, no problem.
Yeah, you should leave actually. This is not open session. Vijit, I am logging out now.
Yeah, okay.
So,
Actually,
you
the
can
mail
continue
it was
Hall
said
3 login है अभी.
check if you can join.
Yes. आपको मैं कोई आएगा. चंदन को बोलो.
Sure. I am logging out. But
बासु सर लॉग आउट हो
videos
गया.
that I saw, they ran properly.
Look
No
forward to
issue.
problems in joining.
Sound quality
Okay, sir.
was also good.
Audio is okay.
Yes. Yeah.
Now I can leave, no problem.
FT तुम्हारा है ना. हॉल 3 ठीक है. और एक वीडियो प्ले करते हैं. Yes. आपको मैं नेक्स्ट वीडियो प्ले करते हैं. चंदन को बोलो.
Sure. I am logging out. But
बासु सर लॉग आउट हो
videos
गया.
that I saw,
16.
they ran properly. No issue. Sound quality was also good.
Yes. FT तुम्हारा है ना. हॉल 3 ठीक है. और एक वीडियो प्ले करते हैं. Yes. आपको मैं नेक्स्ट वीडियो प्ले करते हैं. चंदन को बोलो.
I am logging
Hello everyone, I am Sujit Kumar from NIT Clerk. Today I am presenting my first conference paper on the topic Computational Study of Flow and Heat Transfer Characteristic of Oblique Laminar Slot Jet Impingement on Isothermally Heated Cooking Plate. Now in this presentation I will discuss the following section: introduction, problem specification and methodology, validation of project work, result and discussion, conclusion and references. Let's come to the brief introduction of the impingement jet cooling. The impingement method is one of the efficient methods for cooling of a heated item, heat treatment of the metallic product, tempering of glass, dyeing, textile and food stuff. It also enhances the cooling of efficiency in the electronic industries nowadays. The cooling depends upon the geometrical condition of impingement jets. The flow and heat transfer characteristics of multi-jets can highly differ from a single jet. The main objective of the research is to study of flow pattern and thermal characteristic of laminar twin oblique jet impingement over a moving flat plate, and also to perform the parametric study by varying the following parameters: Reynolds number, velocity ratio, angle of impingement. Now, problem specification. The domain is restricted by two parallel plane surfaces as shown in figure 1. The lower surface is known as impinging surface, and the top confined wall holds the twin slot jet at some inclination with upper surface. The inlet velocity is uniform, and the inlet temperature of jet is 300 K. The normalized dimension is used to define the geometry of the problem given. The normalized width between upper and lower surface and normalized length between the innermost point of the twin slot jet are H and L respectively. This is the schematic diagram of the dome. Here theta is the impingement angle from the upper surface. This is the inlet temperature, and plate velocity is infinity. And total span length is 60 dH. dH is the normalized heteroid diameter of the slot jet. W is the jet width. H is the normalized width of the surface. L is normalized length between innermost point of the twin slot jet, and 0.5 is the normalized hydraulic diameter of the slot jet. The following assumptions were taken while solving the computation. The flow is assumed to be laminar, incompressible, steady, and two-dimensional. The working fluid is air, and its thermophysical properties are assumed constant. The following is the normalized hydraulic diameter of the slot jet. First one is the following calculation of mass means rate of mass entering the system equal to the rate of mass leave the system. The second equation shows the momentum equation in x direction, and the third in y direction. The fourth equation shows the conservation of energy. In the above equation, there are many non-dimensional variables are used, which are following: x, y, u, v, p. The velocity ratio. It is the dimensionless parameter defined by the ratio of net velocity and jet velocity. In this study, the value of velocity ratio is considered in range r is equal to 0 to 2.0. Mathematically, it's given in equation 5, and the local Nusselt number is obtained by the following equation, and Rex is equal to minus d5 by dt in equation 6. And now move to the boundary condition. No slip boundary condition are imposed on the wall. The top wall contains mathematically the impingement jet considered as adiabatic. The impingement plate is considered as isothermal and moving with velocity unit. Both sides of wall flow boundary imposed by constant pressure outlet. The computation of various combination of parameters were performed by taking one parameter as a variable, while others were keeping constant. The combination of parameters was tabulated. The total 75 combinations were computed and results were observed. Now come to the solution methodology. The solution was performed in ANSYS 18.2. An algorithm was selected PSOI, in which momentum and energy discretization scheme power law were selected. The residual was set 10 -6 for all cases. Grid independent tests were performed for the different combination of the grid stationary plate. Four refinement level were selected for the grid independent test. For all cases of refinement, the variation of local Nusselt number curve along its axial length are computed and plotted in figure 4. And peak value of local Nusselt number and average Nusselt number are tabulated in table 1. It can be seen that beyond the third refinement, 24 into 250, the change in Nusselt number distribution is insignificantly. So the grid size 74 into 250 is selected for the presentation. And the figure 3 shows the sample residue in the computation of the flow domain of full domain. Now validation of present work. The strategy is followed to solve the problem include the validation of numerical solutions for the twin slot J impingement. In this, the result were obtained from the given parameter Reynolds number 100, L is equal to 4, H is equal to 8 at different angles at theta, compared with the result of series for a stationary plate condition as shown in figure 5. Overall good match was has been obtained. Now comes in result and discussion section. First we discuss the streamline pattern. Figure 6 and 7 shows the plate and knowledge. It can be seen for a stationary flat condition, the symmetric flow field is obtained when the impedance jet divided into two walls. The formation of multiple recirculation occurs. Figure 8 to 13 represent the streamline pattern for moving plate conditions at different Reynolds number and different velocity ratio, and also at different theta impingement angle theta, in which the streamline pattern different for different velocity, different velocity ratio, and different for different loss of pattern. It can be seen that multiple recirculation are occur in left side. Now comes the temperature control. For a stationary plate condition, symmetrical pattern of temperature distribution observed as shown in figure. The region surrounded the jet has significantly lower temperature, which indicate the existence of recirculation region. Temperature of the domain is more uniform at the case of lower impingement angle. For a moving plate condition, it also seen that the temperature distribution is different at different locations. At lower impingement angle, the distribution temperature distribution is more uniform. In this. Now comes to the Nusselt number distribution along plate length. Figure 20 shows the distribution of local Nusselt number along plate length. It can be seen that at high value of impingement angle, more localized pulling at jet region occur. At lower impingement angle, more distribution pulling occur, and the curve is at an angle 45 is higher than all cases. Hence, for more distributed pulling for stationary plate condition, impingement angle 45 greater. And the figure 21 shows that one of the combination of moving plate condition in which impingement angle is taken as variable. The overshoot and local Nusselt number near the left region indigestion is due to pressure output, body condition, and negligible or small boundary thickness. And figure 20 shows the Nusselt number distribution for various velocity ratio at constant increment angle and constant Reynolds number. And it can be seen that higher velocity ratio, high value of heat transfer angle and more uniform. Figure 23 shows the variation of local Nusselt number for a various Reynolds number, while other parameters are kept constant. And observe that the Nusselt number distribution for various velocity ratio at constant hence heat transfer increases with increased Reynolds number. And figure 4 shows the comparison study of average Nusselt number for different Reynolds number at different displacement angle. It can be seen that when Reynolds number increases, the average Nusselt number increases too, and more heat transfer occurs at greater displacement angle. Conclusion: for a effective pattern of temperature transfer increases with line Reynolds number. The value of theta should be in between 30 to 55. At higher value of Reynolds number, the peak value of NU is shifted toward the jet. As the Reynolds number of the jet increases, there is increase in the value of Nusselt number. This trend event follows when the velocity of the plate increases. For the range velocity ratio, consider the study with increase the plate velocity, the value of Nusselt number jet inlet region decreases. The value of Nusselt number increases with increase in Reynolds number for the given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. Consider the study with increase the plate velocity, the value of Nusselt number jet inlet region decreases. The value of Nusselt number increases with increase in Reynolds number for the given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. Consider the study with increase the plate velocity, the value of Nusselt number jet inlet region decreases. The value of Nusselt number increases with increase in Reynolds number for the given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. Consider the study with increase the plate.
Myself, Dr. Nilon Kumar. I am from Department of Technical.
The value of Nusselt number increases with increase in Reynolds number for a given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. Consider the study with increase the plate.
Myself, Dr. Nilon Kumar. I am from Department of Technical.
The value of Nusselt number increases with increase in Reynolds number for a given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle is at 90. And these are references. Consider the study with increase the plate.
Myself, Dr. Nilon Kumar. I am from Department of Technical.
The value of Nusselt number increases with increase in Reynolds number for a given value of impingement angle. The highest value of average